Hi there guys, good morning, good afternoon, good evening, whatever time it is, wherever you are watching this video right now. And welcome to this video where we're going to take a look at a problem in mathematics that I've selected from this textbook. So it's called Statistical Inference, second edition. The authors are George Casella and Roger Berger. This is quite an advanced textbook. This was one that I used during my undergraduate studies for my mathematical statistics courses that I took. There was only a couple of them, but this book came in quite useful for those courses. For the problem that we're going to be looking at, you don't need to know anything about probability. You don't need to know anything about statistics. Okay, so even though the problem is taken from this book, so presumably at some point, somewhere down the line in this book, the result of this problem comes in useful in statistical theory. We don't need any statistical theory or probability theory to solve this particular problem, okay? All you need really is a knowledge of integration by parts, binomial coefficients, and hence factorials. And as long as you're quite comfortable with algebraic manipulation, then we should be okay. Now, what I would recommend, that this is going to be quite a difficult video for me to make and potentially for you to watch, for the simple reason that it's quite heavy algebraically. Okay, it's not that the concepts are difficult to understand, it's just that there's a lot of the algebraic expressions involved are going to be quite long. What I would recommend is that you take notes, because I'm going to be writing things on the board, then I'm going to be rubbing things off the board. So maybe make notes if you need to. Watch bits again if you need to, whatever, okay? But it's not necessarily going to be a straightforward video for me to make and for you to necessarily watch. Nevertheless, I want to make it for the simple reason that what I'm trying to do with these videos is really to try to describe the problem-solving process in mathematics, what it's like to try to find a solution to a non-routine problem in mathematics. Because what I find, one of the biggest difficulties that I think from my experience for mathematics learners is that they don't necessarily fully appreciate how challenging the problem-solving process is or can be in mathematics. The way, unfortunately, that mathematics is often presented to mathematics learners, particularly at maybe GCSE level, A level, in textbooks and in the classroom, is kind of in a very polished form. So any problems that are presented with model solutions, the solutions are straight to the point. Okay, there's very little discussion or consideration given as to how the solution to that particular problem has come about. And this is unfortunate, because this is an essential part of the problem of learning to be successful in mathematics, is developing the right kind of mindset to solve non-routine problems. What a lot of people kind of get the impression is that solutions to problems should just come out like that problems can all be categorized into certain types, and really it's just simply a case of waiting for somebody to tell you how to solve that type of problem. And then when you're presented with that type of problem, just kind of regurgitate what you've been told to do. But if you're presented with something, a type of problem that you don't recognize, then you've just got to sit and wait for somebody to tell you what to do. But that's not the case, okay? Problem solving is really about using your creativity, generating original ideas, trying to follow those ideas through. And sometimes it can be quite a painful process to actually go through. And that's what I'm trying to capture in some of these videos. So what I've done is I've come across this problem, never seen this problem before, I've never solved this problem before, I've had a go at it, I've had to go through the problem solving process. And what I want to do now is try to articulate to you what that problem solving process looked like for me in this particular case. Okay, and that's all I can do really, is give you some ideas about how you might be able to go about solving problems. I can't tell you how to do it, because there's no systematic way of instructing somebody how to solve problems in general. Okay, It's just something that you have to learn through feel and just intuition in a lot of cases. So it's not like solving quadratic equations where there's a very methodical and systematic way that you can be taught to do that. It's a very different skill. Nevertheless, it's an absolutely essential skill. If you want to be successful at mathematics, you need to have highly developed problem-solving skills. Okay. One thing that, from my experience, is those people that go into mathematics exams with confidence and come out knowing that they've done well and obviously get the high grades that they expect to get, they're the people that typically have highly developed problem-solving skills. Okay, whether they realize it or not, that's usually the case. Okay, so let's have a look at the problem and let's see how we get on with it. So again, I reiterate, there is going to be a lot of algebra involved on the board here. I'm going to be writing things on, I'm going to be rubbing things off. Make notes, rewind the video if you need to, because things will disappear as the video progresses. Okay, so all we're asked to do is to prove this equality. Okay, so hopefully you can see it on the board, but it's the sum from k equals 0 to x. Hopefully you're familiar with sigma notation. If you're not, I'm not going to explain it in this video. Of n choose k times p to the power of k times 1 minus p to the power of n minus k, and that this is equal to n minus x times n choose x times the integral from 0 to 1 minus p of t to the power of n minus x minus 1 times 1 minus t to the power of x dt. Okay, so when you need to prove an equation such as this, there's a very great tendency to kind of focus on the left-hand side, the expression on the left-hand side of the equals symbol, and probably this is just due to the fact that in English, and we tend to read from left to right, as in a lot of languages. So we start to read here, but sometimes in mathematics, really, we need to shift our attention to this thing over here on the right-hand side, and realize that this is just as important as this thing. There's no reason why we should favor the expression that's on the left-hand side, unless it's a definition or something that we're dealing with, in which case the thing on the left-hand side is the thing being defined usually, and the thing on the right-hand side is the thing that is defining the thing on the left-hand side. That's not the case here. It's not a definition. Okay, it's just an equation. But I fell into this trap. Okay, so I was looking at this, and I was thinking, okay, how can I make this into this? And because you've got difficulty here where you've got an integral symbol over here, you've got an integral, but no integrals here. So I was thinking, how can I get an integral into this expression? Rather than thinking, how can I get the integral out of this expression? Okay, and sometimes it can just take you a few minutes just to realize that you need to flip things around a little bit, and it's fine. This is how it happens. This is the whole point of these videos, to illustrate that these things happen. They're normal. It's just you've got to be prepared to be a bit flexible with your thinking. So while I was still thinking about this, one result that kind of came to mind, which is a result that it was a problem that I went through in another one of my videos. At the time of uploading this video, I may not have uploaded that video. Nevertheless, I've made it, and the result is that the integral from 0 to 1 of x to the power of n 1 minus x to the power of m dx is equal to, let me get this right, m factorial times n factorial over m plus n plus 1 factorial. I was thinking maybe this could be quite useful for the simple reason that binomial coefficients and factorials quite closely related. and you seem to have the integral here, but no integral here. Maybe there's a way that I can kind of slip an integral in here somehow. This idea didn't seem to bear any fruits, so I kind of gave up on it. So I'm not saying, that's not me saying that the idea couldn't work, okay? I think it would be possible for you to start with the expression on the left-hand side and derive the expression on the right-hand side here. But I think to do that, it would help if you had a bit of insight into how the problem, how the solution to the problem is going to go in the first place. So what we're trying to do here is actually find a solution to this problem. But actually, once you kind of know that, then it's probably going to be easier for you to see how you could go from this side to this side. But in the absence of such a solution, or at the absence of such a knowledge of a solution, it turns out it's easier to start with this thing over here, okay? So that's what we're going to do. So I didn't pursue this idea any further. I just kind of shelved it. I'm not saying it doesn't work or it can't work or anything like that. It's just I didn't pursue it any further because I came up with a different idea that I thought was going to be better. Okay, so something that I'm going to make you aware of. I've got my notes here, by the way. I am going to have to refer to notes throughout this video because there's a lot of algebra involved. I want to make sure that I get it right. Just a bit of a heads up. I didn't notice this. I didn't know that these were going to be useful from the outset, but I'm going to present them now because I am going to use them at some point. And that is that this here, n minus x times n choose x is equal to, and I want to get it right, x plus 1, n choose x plus 1. It might be worth making a note of these things, by the way. We've also got the n minus x plus 1, n choose x minus 1 is equal to x minus 1, x n choose x. Okay, so notice here that the n minus x plus 1, this is n minus x minus 1, just to be clear. So in general, what we have is that n minus r, n choose r, is equal to r plus 1 times n choose r plus 1. Okay, this is a result that is going to be very useful to us as things progress. So make a note of this. Now, I did not know that this was going to be useful from the outset. This was something that I had to figure out was going to be useful. In fact, I had to figure this result out. Now, there will be people watching this that will know far more about binomial coefficients than I do, okay? That have studied binomial coefficients or come across the various properties of binomial coefficients and things like that. I don't know everything about them. Nobody knows everything about them, but it's just one of those things that I've used binomial coefficients to a certain extent, but I've never really got deep into combinatorics and things like that might use binomial coefficients a bit more. So this property of binomial coefficients wasn't something that I knew off the top of my head. I had to figure this out. This is part of the problem solving process. It's really important that you understand this, that sometimes, yes, you have to reinvent the wheel a little bit when you're trying to solve a problem. You've got these little sub-problems that you're presented with and you have to deal with them, okay? You have to figure them out, figure out that this is actually a problem, and then you have to find a solution to that little sub-problem, and that there's nothing you can do about this. I'm sure that somewhere in some mathematics book somewhere, this result will be stated, and it's there with its proof. I'm going to go through the proof actually in a second, but I don't know where it is. I don't know this result off the top of my head, or I don't recall it accurately enough, or whatever. So I've got to figure it out, and I had to prove this result myself. Okay, and you've got to be prepared to do these sorts of things. So let's just have a look how this is going to work. So we start with n minus r times n choose r. So this is equal to n minus r times n factorial over r factorial n minus r factorial. Just pause here for a second, because something that I know is a big problem for a lot of A-level students when it comes to binomial coefficients is that they don't know how to express binomial coefficients in terms of factorials. And even if they do, they're not very good at manipulating factorial expressions, right? They've not really fully grasped the idea. I mean, a factorial is called a factorial because of the factors, right? So you really need to, the language is important sometimes because it gives you clues as to what's going on with the expressions. And this really comes from the fact that a lot of the time when A-level students in particular who have come across binomial expressions, binomial coefficients fairly recently, to them binomial coefficients are just something that their calculator spits out at them. So they put in to their calculator something like 9 choose 5, and a number pops out. Oh, that's 9 choose 5. And they don't realize that 9 choose 5 has to be calculated in a systematic way. It can be expressed in a systematic way using factorials. And this really, really affects their ability to understand how binomial coefficients can be manipulated and to exploit the various relationships between binomial coefficients of different forms. Okay, so really make sure that you know and have a bit of experience at working with factorial expressions that represent binomial coefficients, because what I can see I can do here is I can cancel this n minus r. Remember, n minus r factorial is n minus r times n minus r minus 1 times 2 times 1. So this is n minus r factorial. So I've got the factor of n minus r. So that will cancel. And what I'm going to be left with is n minus r minus 1 factorial. Okay, so what I can do now is something that you've just got to be prepared to do these sorts of things from time to time. What I'm going to do is I'm going to multiply the numerator and denominator of this by r plus 1. How do I know to do that? Because first of all, I've seen things like that done before. Second of all, I know that stuff like that can be useful. But how did I know it was going to be useful here? Well, I didn't until I tried it out. Okay, but it's got something to do with what I've got here, because I recognize, even though I've written this as n minus r minus 1, I recognize this as n minus r plus 1. Okay, so this is not quite the form of a binomial coefficient, but I see that there's something that I can do to make it into the form of a binomial coefficient. And this is really important. Being able to spot these kinds of patterns is really important. And this takes a lot of time and a lot of work to develop this skill. So I'm not going to say that to spot these patterns, you just do this, or you just do that, or you just do the other. It's just something that you have to develop a feel and an intuition for. And either you do or you don't. It's as simple as that. So here, if I multiply numerator and denominator by r plus 1, I get r plus 1 times n factorial over r plus 1 factorial times n minus r plus 1 factorial, which is equal to r plus 1 times n choose r plus 1, which is exactly what I need here. Okay, so again, these are going to be really, really, really useful to us as we go on. So so much so I'm gonna actually make no, we'll leave it at that. Hopefully you've made a note of it. I've got them here on my notes, so we're fine. Right, so let's start over here then. So n minus x, n choose x, times the integral from 0 to 1 minus p of t, n minus x minus 1, 1 minus t to the power of x dt is equal to, now it's going to be n minus x, n choose x times something. So what's going to be the something? Well, I'm going to use integration by parts here. So hopefully you're familiar with integration by parts. What tells me to use integration by parts here? Well, there's a couple of things. First of all, it's a product, which doesn't force things. Doesn't mean that integration by parts is absolutely going to be the thing that I need to use, but when you're trying to integrate something that's an obvious product of functions, then can suggest that. But also, some of you may have come across the idea of reduction formula. In fact, I've kind of alluded to it already in this video when I wrote on the integral from 0 to 1 of x to the power of n, 1 minus x to the power of m dx equals whatever. That formula, that equation that I wrote actually comes about through a reduction formula. And it was this that kind of made me realize that rather than trying to go from here to here, it's going to be better for me to go from here to here, because I thought maybe I can exploit the properties of a particular reduction formula to express this, to kind of change the powers, to maybe reduce one or the other of these powers gradually to 0. Maybe reduce the power of this to 0, and then I can somehow get rid of the integral, because this is one of the good things with reduction formulae is that generally once you've got your reduction formula, you don't really have to do any significant integration, but you can actually get rid of the integral. Plus, also notice that this is a definite integral as well, so you've got limits, which means that you should be able to get rid of the integral at some point. Anyway, there's just a few clues there that are suggesting things to you, and it's important that you pay attention to these. Whether they actually turn into something useful, that's an entirely different issue, but you're just picking up on little clues here and there, comparing what you see in front of you to things that you might have seen previously. And this is why it's essential to learn to solve problems. You have to solve a lot of problems. And I don't mean that you watch somebody solve problems. I mean, that might seem a bit ironic that I'm solving a problem here and you're watching me solve this problem. It's fine to watch people solve problems, but at some point you have to get your hands dirty. Okay, you have to get stuck in. You actually have to solve problems, and you've got to solve a lot of them, because you need to start forming these patterns in your mind, these experiences where you come across something that's going to be useful to you at some indefinite point in the future, but which your mind can refer back to in some way. So you can recognize, oh yeah, I've done something like that before, which is, for a lot of the stuff that I'm doing here, when I was talking about multiplying numerator and denominator by r+1, because I've seen that done before. And somewhere deep in my mind, my brain was telling me that's possibly going to be useful. Try it out. Okay. So what do we get? Well, one of the problems that you're presented with when it comes to integration by parts is that you need to assign u and dv by dt. Okay. In fact, I'll give myself a little bit more space. So you've got two functions here. One you need to assign to u, the other to dv by dt, either that way round or that way round. Okay. Which way round? Well, sometimes what you're looking for, remember with integration by parts, you've got the integral of u dv by dt equals uv minus the integral of v du by dt. When you use integration by parts, you transform this integral effectively into another integral plus a little bit extra. what you're hoping is that the new integral is in some way simpler than what you started with. Okay, it might not be simple enough for you to actually do the integration at this stage, but hopefully it's simpler. Okay, that tells you that something's going in the right direction. Because if you get this wrong, what you end up with here is more complicated than what you started with. It's not wrong, it's not incorrect, but it's just not useful to you. Okay, theoretically it's fine, but it's just not useful to you. So, as you get a bit of experience with integration by parts, you'll start to predict which way round to assign the u and the dv by dt. Now, some books, some teachers will try to tell you that, if you've got a product of a power of x with an exponential and you assign them this way around, and if you've got a trigonometric function and an exponential and you assign them this way, if you're relying on stuff like that, you've not had enough practice with integration by parts, because it shouldn't be. It should be something that you kind of have a feel for which way round to assign the u and the dv by dt, and it does come with experience, because you can start to predict without even writing anything on the page which way round the u and the dv by dt should be assigned, so that you end up with something simpler. Now, it doesn't. Sometimes it's a bit ambiguous, so here it could kind of go either way. And in that case, well, just be prepared to try things out in both possibilities. There's it's just as simple as that. Okay, it shouldn't be any reason, if you can't decide which way to assign the functions, that shouldn't be any reason for you to just stop or anything like that. It just means that you're potentially going to have to try them out. So I didn't know. I had an idea which way to assign them, I guess, but I didn't know for definite, so I just thought, well, I'll give it a try. I'll just assign u is 1 minus t to the power of x. In fact, no, I didn't do that. I did it the other way around first. I did t to the power of n minus x minus 1. dv by dt is 1 minus t to the power of x. So I got du by dt and I got v equals whatever. I'm not going to do it for the simple reason that this didn't work. It didn't take me in the kind of direction that I was wanting to go. Okay? And that's how it is sometimes. If something's not working, scrap it. Go on to something. If you've got two possibilities and you try one and it doesn't seem to be working, scrap it. Go for the other way. Okay? Sometimes you just have to be a bit ruthless, and just because you've chosen to take one course of action doesn't mean that you have to stick to that you can't change your mind or anything like that. Sometimes you've got to. So this didn't work too well. Assign them the other way around. So u equals t to the power of n minus x minus 1. This to 1 minus t to the power of x. So what do we get? du by dt, and we are differentiating with respect to t here. Is going to be n minus x minus 1. I think I've written them the wrong way around again, haven't I? Yeah. Okay. Let's get it right. 1 minus t to the power of x. T to the power of n minus x minus 1. Right, that's better. So in this case, differentiate that, I get minus x, 1 minus t to the power of x minus 1. V is equal to, t to the power of n minus x over n minus x. So u times v is going to give me t to the power of n minus x, 1 minus t to the power of x over n minus x, minus the integral. And okay, it's minus, so that's going to end up being a plus. V times du by dt. Bring out the constants. N minus x. What do I get? T to the power of n minus x. 1 minus t to the power of x minus 1. Okay, and this is really useful because this power has been brought down by 1 now. Okay. So what this suggests is that I can kind of iterate this approach. x times maybe. And eventually this power is going to end up at 0. And that's what I'm aiming to do now at this stage. Oh, that was a bit careless of me. I forgot the limits. 0, 1 minus p, 0, 1 minus p. So we've got definite integrals here. So this is equal to n minus x, n choose x. It's going to be, here we're going to have t to the power of n minus x. Sorry, putting the limits in, so it's going to be 1 minus p, of course. 1 minus, I told you this was going to be a difficult video to make. 1 minus p is just p over n minus x plus x over, sorry, n minus x times n choose x times x over n minus x, the integral from 0 to 1 minus p, t n minus x, 1 minus t, x minus 1 dt. Now here's something that's really useful. It happens, that cancels with that, and that cancels with that. Okay, so what I end up with here is just n choose x, p to the power of x, 1 minus p to the power of n minus x, which is exactly the right form for what I've got here. That's one of the summands here. And then over here I'm just left with x times n minus x. So I'm going to tidy this up a little bit. I'm not going to rewrite the whole thing out. I just want to tidy it up a little bit. Get rid of that. Get rid of that. Get rid of this thing. In fact, n choose x times n choose x. Okay. Okay, so that's where we're up to. Now, I anticipated a bit of a problem here. I'll explain what that is after I've had some coffee. Up here, if you notice, I had n minus x times n choose x. Okay, and I got some cancelling out. But when I went through the integration by parts, I ended up with this here, x, n choose x. And I was kind of projecting forward a little bit and thinking, what are things going to be like? What do I expect things to be like when I do integration by parts again here? I didn't know exactly what it was going to look like, but what I anticipated was that I'm not going to get the cancelling that I need. Okay. Nevertheless, I kind of went through it just to see what happens, and sometimes you've got to do that. You just got to plow through anyway. You might anticipate that there's going to be an issue. Either it turns out that it's all in your head, that the issue doesn't actually exist, or there is an issue and you've just got to deal with it. Okay. Or, well, I suppose there's a third option, which is there's an issue and you choose not to deal with it. Okay, but we're trying to solve problems here. We want to solve the problem. That's our goal. Okay, if your goal is not to solve the problem, then don't watch this video. So, our focus now is on this thing here, really. So, let's have a look. X, n choose x. The integral from 0 to 1 minus p of t to the power of n minus x, 1 minus t to the power of x minus 1 dt. This is going to be equal to x, n choose x. And we'll go through again, okay? So u equals 1 minus t to the power of x minus 1. Because I differentiated the 1 minus t bit the first time round, I need to keep going in that direction, okay? So again, assigning the u and the dv by dt, there's got to be some consistency there. I differentiated 1 minus t to the power of x here. I need to differentiate the 1 minus t to the power of x minus 1, because if I don't, all that will happen is I just end up back where I started. So what does that give me? du by dt is going to be minus x minus 1 times 1 minus t to the x minus 2. dv by dt is equal to t to the power of n minus x. V is therefore equal to t to the power of n minus x plus 1 over n minus x plus 1. So here I get u times v, t to the power of n minus x plus 1, 1 minus t to the power of x minus 1 over n minus x plus 1, between 0 and 1 minus p, minus the integral from 0 to 1 minus p. Again, I've got minus here, so it's going to be plus. Bring the constant straight out just to save any faffing around. So it's going to be x minus 1 over n minus x plus 1 integral of v times du by dt. So it's going to be t to the power of n minus x plus 1 times 1 minus t to the power of x minus 2. Again, you can see the power dropped by 1 again. That's a very good sign, okay? Right, so now, expand all of this out, what happens? I get x times n choose x times, plug the limits in, 1 minus p to the power of n minus x plus 1. P to the power of x minus 1 over n minus x plus 1 plus x minus 1, x times n choose x times x minus 1 over n minus x plus 1 integral from 0 to 1 minus p t n minus x plus 1 minus t x minus 2 dt. Okay. So what I anticipated was going to happen kind of has happened. I don't seem to get the cancelling out that I did up here. Okay, so remember the n minus x was cancelling all over the place, and it was great. But it's not now. What's the problem? Well, do you remember I gave you some identities right at the beginning? One of those identities was that n choose x is equal to n minus x plus 1. N choose x plus 1. X minus 1 even. So it took me a while to figure this out, okay? That this is what I needed to do, because sometimes you just don't see, straight away what you need to do. And this is part of what you have to get used to. One of the difficulties that you will encounter when it comes to solving problems is that you just have to be patient. You have to really think things through very carefully. And again, one of the problems with how mathematics is presented in the classroom and things like that is that people come away with the impression that solutions to problems just kind of flow out automatically, and kind of the solutions kind of write themselves, and it's just not the case at all. It just does not work like that. So what I can do is I can replace this x times n choose x with this expression, and what's going to happen then? Well, the n minus x plus 1 is going to cancel, so replace that with this. That's going to cancel with that. What am I going to be left with? N choose x minus 1. So rather than rewrite the whole thing out, I'll just tidy it up a little bit. I'm just going to be left with n choose x minus 1. A similar thing over here. Replace that with that. What happens? Cancel, cancel. What am I going to be left with? X minus 1 times n choose x minus 1. Okay, so here we get a big thumbs up again, a big green light, because look, this is again of the right kind of form that we're looking for. N choose x minus 1, 1 minus p to the power of n minus, remember that this is n minus x minus 1 in brackets, p to the power of x minus 1. So exactly the right form. The only difference is that I've just written these the other way around. That's insignificant. Okay, but it's other than that, it's exactly the right form. So this is giving me the big go ahead, really. Continue this, just keep going. So remember now that this expression here replaces this expression here. Okay, so all of this here replaces all of that there. So now we've got that plus this. So if we continue this now, what we get is that n minus x, n choose x, integral from 0 to 1 minus p, t to the power of n minus x minus 1, 1 minus t to the power of x dt is going to be equal to, so it's going to be n choose x, 1 minus p to the power of n minus x, p to the power of x, plus, and so I'm going to miss out all of the intermediate steps, and I'm going to refer to my notes. We end up with, right down at this end, n choose 1 times p to the power of 1, 1 minus p to the power of n minus 2, is that right? Sorry, n minus 1, of course, yeah. So they need to add up to n. The powers need to add up to n. Plus 1 times n choose 1, the integral from 0 to 1 minus p of, and we just end up with, I'll write it in, I don't really need to, 1 minus t to the power of 0. So now the power of 1 minus t is reduced so far that it's at 0 now. And then we get t to the power of n minus 1. Now the difficulty here for me was actually just figuring out exactly what all of the powers and everything like that was going to look like, and that's just spotting the pattern and making sure that you've observed the pattern carefully enough that you see. I didn't get it right first time, by the way. I did muck up one of the powers here or one of the powers here first time through. It happens, you know. It's just try to just carefully observe what you see. So then everything's good, right? Notice that we need to sum from k equals 0 up to x. Well, here we're effectively summing from k equals 1 up to x. So there's just this to sort out, really. So let me just drag that over here. So we've got the integral from 0 to 1 minus p. Forget about the 1 minus t to the power of 0 now, because that's equal to 1. T to the power of n minus 1 dt. This is going to be equal to integral from, sorry, not integral. It's going to be t to the power of n over n between 0 and 1 minus p, which is 1 minus p to the power of n over n. Yeah. Okay, so 1 times this, 1 times n choose 1 of this is equal to, n choose 1 is n. So it's going to be n times this thing, n times 1 minus p n over n, which is 1 times 1 minus p to the power of n. And now I want to make this exactly of the right form. Okay? So I've got to fiddle things a little bit. Obviously in a legitimate way. You know, whatever manipulations I make, they've got to be legitimate manipulations. So 1 is equal to n choose 0. Okay? 1 minus p to the power of n times p to the power of 0. Okay? So in other words, this, I missed something off there, didn't I? It should have been 1 times 1 n choose 1 integral from 0 to 1 minus p of t to the n minus 1 dt. Looks like I got a bit giddy there. Okay, so this bit here can be replaced with that. So let's do that. Let's get rid of this thing. And what am I left with? N choose 0. I'll write it around the other way just so it matches. Okay, so what have I shown? I've shown that this expression on the right hand side up here is equal to this sum, which everything's of the form n choose k 1 minus p to the power of n minus k, p to the power of k. So I can sum from k equals 0 up to k equals x. And that's it. Magic. We're done. Okay, so it's been a difficult video to make. This was my second attempt actually at making this video. The first attempt I got into all sorts of tangles. So I knew it was going to be a difficult video to make. So hopefully you've kept up with everything. If there is anything that's not clear that you're unsure about, feel free to leave a comment in the comments section. What would be really great is if you can hit the subscribe button. This is a very small YouTube channel at the time of making this video. I really do want to reach out to help people develop their mathematics skills and develop their problem solving skills. So if you know anybody that would find these videos useful, or you think that they might find them useful, please share these videos with them. Hit the like button, leave a comment in the comments section. If you do need any help with anything, with your mathematics studies, particularly if you're applying to university maybe to do mathematics and you've got to prepare for a STEP exam or an MAT exam or something like that, feel free to get in touch. Or if it's just your normal maths and further maths A-level exams that you need help with, feel free to get in touch. I'd love to have a discussion with you about what your needs are, what your requirements are, what your expectations are, and have a discussion with you about how I can help you. I'd love to hear from you. So that brings us to the end of this problem, and it brings us to the end of this video. Thanks for watching, guys.